So in calculus we look at rates and we look at accumulations. This graph is the rate of nuclear weapons testing worldwide from 1945 to 1998. And it shows for any given year along the bottom how many tests were conducted in that year. So we can think of the heights of these bars as the rate of weapons testing averaged over 1 year. Our task here is to look at a range of dates and see if we can estimate from the graph what the average number of tests per year was. If we look at an individual year like 1962, where it's the highest here, so I'm drawing a line up 1962, you can see that its height is about somewhere around 175. So the average rate in 1962 is about 175 tests per year. Now let's look at something a little bit more interesting. What about if we start at 1965? That's here. And we end in 1980, which is here. All right. In that interval, I want to know what is the average number of tests per year. The unit that we're talking about is the same. It's still going to be tests per year, but we don't have just 1 year we're talking about now. It's a whole bunch of them. So visually what we do is we look at this graph and we try to find the point where if we drew a line across those from 1965 to 1980, if I could take all the stuff on top and chop it off and fill in all the holes and make a perfect rectangle, then I would have exactly the average rate. So visually, if we look at it, and again this is just an educated guess, but your eyeballs are actually pretty good at this. It looks like it's somewhere around there. And if we extrapolate over, go all the way over to the left, we have maybe 60, something like 60 tests per year. We can find the actual numbers that go with these graphs at a site called Natural Resources Defense Council, and it's in these tables here, which I'm going to pull out and put into a spreadsheet. So I've taken the numbers off those tables and just extracted the total number of tests for the years we're interested in, 1965 through 1980, and we want to know what the actual retail average is. To find an average of the rate per year for all these years, we just need to add up all the tests. So I'm going to compute sum of all these rows, and that says there were 947 tests from 1965 to 1980. How many years is that? Well, you might think it's 15, but it's not. It's actually 16. Let's count the rows. So we have 947 tests, 16 years, and we divide, put a line there to get the rate. And the rate is 947 divided by 16. We get 59.1, which is very close to our guess of 60 tests per year. Very important. Put the units on there. So there we've shown visually as well as numerically how to compute an average rate. For practice, let's look at the years 65 to 80 again and the number of nuclear tests shown on the graph. See if you can identify the 3 consecutive years within that range that have the highest average rate of nuclear testing and the 3 consecutive years that have the lowest average rate. Then try to estimate from the graph what those rates are, and then check your answer using the data. Notice how much easier it is to look at the graph and make an assessment than it is to look at these numbers in the column. You will want to rewind the video and look at the graph to make your calculations and then come back to the data. I have uploaded the data to the Moodle site so that you don't have to type all these numbers in. Look for a file called test data. So I'll show you how we can find the answer to that problem using Excel visually. Let's look at our data here again, and I'm going to create a new column called the 3-year rate. Okay? And what we're going to do is take any 3 consecutive years and find the average rate of testing for those 3 years. So the first entry will be 65, 66, and 67. The next one will be 66, 67, and 68, and so on. So I'm going to do that in this column here. So the way I'll calculate that is equals average of these three numbers. And then I hit Control Enter to fill in all those cells. I'll clean up the numbers a little bit. And we can scan this to see when the biggest and the lowest is. So let's see if you get the same answer. We've got two 70s and a 73. It looks like 73 may be our high. And the low is going to be 49. We could also look at this visually to actually graph the rate. If I highlight this rate column, and we can see that the highest one is in 1966, which is what we got, and the lowest one is in 1973, which is what we got, and those are the numbers. The next thing we want to look at is the accumulation graph. In calculus, we look at rates and accumulations. So for the example so far, we looked at the rate graph, which is right here. I've reproduced it on an Excel graph, and I got all of the data off of that site we looked at. So this is kind of an ugly version of that earlier graph, you can see. We're going to call that N prime. Once I have the data, it's not hard to make the accumulation graph, because here in 1945 we start with 1. This was the number of tests in 1945, the rate for that 1 year. The next year there were 2, so there were a total of 3, 1 plus 2. The following year there weren't any, so the total remains 3, and then add 3 more and you get 6, and so forth. And if you add that up all the way down to 1996, then you get this graph here. This is the accumulation graph. I'm calling it N of t. It does not have the prime on it. I've switched from bar graphs to line graphs here to make it look cleaner. And let's re-examine our question about average rates. With the bottom graph, we have the rates given to us, so it's easy to find an average. We can just add up and divide by the number of years in the interval we're interested in. But in the top graph, we have the accumulation, and in calculus we'll call that the integral. The top graph is the integral of the bottom one, or the bottom one is the derivative of the top one, which we denote with this prime. Let's look at a specific interval. If we look at 1963 to 1972, for example, 1963 on the data, 1972. And we want to know what's the average rate of nuclear testing for that period. Again, if we use the table in this middle column, or the graph, when we're actually looking at rates from 63 to 72, it's quite easy. With the data, we would just add them up and divide by how many there are, and with the graph, we visually try to assess the balancing the bumps above the line with the bumps below the line to make them match. But if we're looking at the accumulation graph, the rate of change looks a little different. This is a familiar problem from college algebra. 1963 to 1972 traces out a span on the graph that looks roughly like that. The rate between 1963 and 1972 is the slope of that line. So the slope of this line is the same as the height of the bar on the graph below. So this is two ways of looking at the average rate. To review this, we can either find the average rate between 1963 and 1972 by averaging the numbers here, or by using the slope formula on the numbers in this column. Now, the advantage of the latter method is I only need the last and the first numbers to use the slope formula, whereas with the rate information I need all of them. It's not that one method is better than the other. It's always good to have two ways to solve the same problem, and we'll see how powerful that is in just a moment. So let's actually do the math here. In the middle column, we can just average these guys up. I'm going to find first the sum of those 10 years. Okay, that's the sum. So this is the rate column. And then we'll divide that by 10 because there are 10 years there. Alright, so we know the average rate from 1963 to 1972 is 62.8 tests per year. Now let's do the same thing with the accumulation column. The way the accumulation column works is we start with this number here, 550. We add all those rates, annual amounts, and then we end up with that one. So we start with the number in 1962 as our base, even though it's out of range, and we add the next 10 years accumulated annual changes, and we end up with a total accumulation of 1178. So it follows then that the total we need to work with, if we're looking at the accumulation table, actually the difference between the end point and the beginning. It's also 628. Okay. So we want to divide that by 10, and we get the same result. So we know how that works now, and the difference is if we have the rates data, we do a straight average. We add them all up, we divide by the number. In the accumulation column, what we do is take the last one minus our base, which is the one before the first one, and we divide by the number of years. And that, in mathematical terms, looks like a slope formula. That's what we'll look at next. So using the rate column, we average rates for 1963 through 1972. For the accumulation column, we use the slope formula to find the slope between years 1962, which is our base year, and 1972. For practice, try this yourself. Find the average rate of nuclear weapons testing from 1976 to 1990 using the rate column, and then try it again using the accumulation column. Stop the video until you're done. If I use rates, the rate column, then I want to average all the rates in the highlighted zone there. And if I want to use the accumulation column, then I have to use the slope formula and use this base. This is where we start, and then we add all those up, and we end up with that number. So the accumulation is the change in Y, or the change in the number of total nuclear weapons tests, which is the number on the end minus the base number at the very beginning, divided by the number of years in that interval. So let me just put count because I don't know how many there are. And we get the same thing. The reason all this is important is because if we take these two methods for solving the same problem and put them together, we get something called the fundamental theorem of calculus.